Hello everyone, I'm very glad to have this opportunity to participate in a Black Hat security meeting, and it is also a great honor to share our achievement here. Today, my topic is attacking and defending machine learning application of public cloud. My presentation is going to focus on three topics. First, the attack method for the classification service of public cloud. Next, the combination of adversarial attacks and the characteristic of cloud service. And the last, introduce the procedure and method that required for a secure development of machine learning application. This content above can reduce the serious attack problem AI service currently facing. Briefly introduce our team's field of work. The direction of our work is AI model security, including research on the model attack and defense methods, and also provides solutions to security risk of various AI applications like fake face detection and model robustness evaluation. They are included in the AI Security Toolkit ADV box. We also have several heavyweight security projects, such as Masalinks, OpenRasp, and most of them are placed on GitHub as open source. The following is the main topic of today's discussion. First, we will show the attack against the machine learning application, and then introduce defense and mitigation measures. These two aspects will comprehensively illustrate the security development process of machine learning service on public cloud. At present, when AI brings us convenience and a surprise, because of the existence of adversarial example, the safety of AI has to be mentioned and discussed. While AI application ranges more widely nowadays, AI safety will become the first need of consumers. Various image analysis methods emerge from the earliest stage of image classification to object detection, 3D detection, semantic segmentation, fake face, etc. Among all applications, image classification is the most essential part of image analysis. Most IT companies provide image classification service, and most of them can be displayed through Cloud API. For example, you can upload an image to ask Google, what is it? And it will give you a right description of the image you sent, in this case, a cat. However, at the same time, an attacker can make the cloud believe that it is a dog by simply adding some carefully constructed noises to the original image. Such image sample is called the adversarial example, which aims to fool AI classifiers. Generating adversarial example is not as easy as it sounds like. It is a difficult task, and it becomes more complicated if you want to influence multiple cloud classification services at the same time. But our method is able to create one adversarial image that is misclassified on multiple cloud services. The security of AI model comes from the transparency of its important information, such as network structure, parameters, and the input. If all of this information is opened, it will be an open entry for an attacker. They can easily generate an adversarial example against the model. In that case, we call it the white box. When the original image is modified, the cause of image distortion is very small, and it is almost impossible to find any attack trace. So, unless the AI model is for education use, white box should be avoided, especially model for commercial uses. Using a white box model is very dangerous even for transferable training. The opposite of the white box is the black box model, which attackers don't have the access to critical information of the model directly, but he can repeatedly try to verify the effect of attacks and guess the important information of the model. That is also very difficult. Unlike password, which can be used repeatedly once it is cracked, the value of a single adversarial image is negligible, It is like cracking one encrypted message by brute force. The significance is low, but the cost is extremely high. The AI services on cloud are also a type of black box model, but they have less information and more limitations than the black box model we talked about. Besides unknown structure and parameters, the pre-modification applied on input is also sealed, like clipping, filtering, and affine transformation. There are many bottlenecks for using repeated attack to obtain extra information of the model, because the model can set a restriction on the requested frequency. The cost and difficulty of the attack will be enormously high in that case. Understanding the difficulty of attack, let's look at some common methods of cloud-based attack. First, attacks based on query, which repeatedly request the service thousands of times. Although we can't get the gradient of the model directly, we still are able to obtain some important information of the black box model. However, it takes more than 1,000 requests to reveal a portion of a model using low-resolution images. The cost of using high-resolution image is several times higher. The second method, transfer learning attacks. The adversarial example is transferable under similar DNN structure. The work of Dan Song has verified this statement in 2016. The comparison chart in the paper is cited here. It shows that an adversarial effect can be transferred to some degree by using similar methods to train the model with similar function. But the challenge is how to find the open source model that are similar to the model on the cloud, because parameters and the structure of the model are hidden. Attacking on cloud-based AI service has certain conditions. Some of them are very difficult to achieve. Is that saying that cloud services are safe enough? I would say probably no. Here is an example of using our method against the cloud classification services. This is a British long-haired cat. Google image classification gives the right answer. This is an adversary example generated by our method. Although it is impossible to get the model information from Google, the attack is still successful. Even though there are some perturbation and distortion, the difference between the adversary example and the original image is not very large. How did we do that? Here is some feature of our method. First, we used a loss function to compute feature similarity and define it as FFL. FYI, it can increase the transferability of attacks. Next, we built a small dataset to train the model, and for each image in the dataset, we send it to the cloud-based service no more than 2 times. Finally, we use a white box model generated by AutoDL to replace the cloud-based service. Generally, our attack involves 2 steps. First, we use the result of Cloud API to construct a small amount of dataset and use it to training the substitution model. Second, we use a substitution model to generate an adversarial example with better transferability. Now, I will introduce the process of these steps in detail. Notice that the substitution model here is trained to produce the results that are similar to the result from the real one, but only in certain categories. The substitution model is only retrained for the categories that need to be attacked. Its features in this category are expected to be more similar to the target model. So when we use non-target attack, if we want to use cats to attack, then we only need a binary classification, a cat or not a cat. We fix the parameter of the feature layer and train only the full connection of the last layer. The training process can be described as follows. We determine the category of attacks, select the attack image, and integrate those images into our training set, which can have dozens or fewer. Those images are labeled by the cloud service. Then the small dataset is successfully constructed. To reach the output of binary classification, we also need image of other animals in the training set. Training substitution model takes time, of course, but it is independent from the cloud service, which is saying that there is no way for defenders to interfere this step. Because the dataset is very small, and there are only two target categories, too many parameters will increase the risk of overfitting, and the features are not likely to be robust. Therefore, to make the feature extract the substitution model more robust, we decided to reduce a certain number of parameters. As for creating adversarial examples, we propose a loss function called FFL for PGD attacks. It is used to improve the success rate of transferable attacks between different models. The traditional PGD attacks only use classification loss, focusing on model classification errors. We increase the loss of multi-layered features to ensure that these features are more different than the one generated by a traditional PGD attack. In addition to classification loss, we will choose the output of multiple convolution layers. The features of different convolution layers represent the semantic content of different dimensions. We choose several different convolution layer features to propagate the features weight at different levels. In different convolution layers, the first one is to recognize the edges and the lines mainly. In the last convolution layer, it recognizes high-dimensional features such as eyes and noses. Lastly, dataset and preprocessing. Since the category to attack is the cat, we select 100 images of cats and 100 images of other animals from the ImageNet dataset. All images are clipped to a fixed proportion and format. We don't have a validation set here. The images for attack are also selected from the training set. In our experiment, the ResNet 152 has a higher accuracy rate, so we choose ResNet 152 as our substitution model. Using traditional PGD and FFL PGD method generate adversarial examples. Compare them to find which one has better transferability. In addition to compare the transferability, we should also pay attention to the gap between them. We need to measure the degree of distortion of adversarial examples. If the images are quite different from the original one, it will lose the meaning of the attack. So we use the peak signal to noise ratio (PSNR) to measure the quality of image and SSIM to measure the similarity between the original image and the adversarial examples. First, look at the escape rate of them. We choose Amazon, Google, Microsoft, and Cloudflare as the target of attack. The average success rate of FFL PGD in these 4 different classification services is more than 90%. The classification service of each platform has a higher success rate with FFL PGD method. It can be shown that FFL PGD has better transferability. Finally, we conduct a set of comparison to verify the transferability of using assembled model attack method. The method assembles many different models to generate adversarial examples, and we use it to compare our method. The baselines here are VGG, ResNet, Inception, and other models. We can see that the basic success rate of this cloud classification service is less than 50%, which is much worse than our method. It is still very difficult for the traditional transferability method to attack the cloud classification service successfully. The previous introduction of cloud attack using FFL PGD shows that the cloud services are still not robust under the attack. Later, we will introduce the defense and the mitigation method of the model. The adversarial attack mitigation has 2 types of defense strategies. The first one is reactive, which is to detect adversarial examples after deep neural networks are built. For example, adversarial detection, input reconstruction, and network verification. The other is preactive, which is making deep neural network more robust before adversaries generate adversarial examples, like network distillation, adversarial training, and classifier robustness. The above methods are all based on the white box security defense. Some of them use a sophisticated gradient masking, or input reconstruction method. But this gives a false sense of security in defenses against adversarial examples, and they can be destroyed by improving attack techniques. The only defense significantly increased robustness to adversarial examples within the threat model proposed is adversarial training. Considering the realization difficulties and the actual effect, we recommend using input reconstruction in the data preprocessing stage and adversarially trained model in the model prediction stage. At the same time, adversarial training included adversarial examples in the training stage and generated adversarial examples in every step of training and inject them into the training set. On the other hand, we can also generate adversarial samples offline. The size of adversarial samples is equal to the original dataset, and then retrain the model. Using our defense technique can effectively resist known spatial attacks, such as Gaussian noise, salt and pepper noise, rotation, and monochromization. Robustness evaluation is used to understand the robustness characteristic of the model in the actual environment after the model training is completed. Using multiple methods, according to certain conditions, to generate examples with a limited virtual difference from the original image. But it is possible to make the model predict the wrong labels to evaluate the robustness of the model in these environments. It can be of two types. The first is safety-related, using adversarial examples formed by spatial transformations or image corruptions, such as scaling, light transformation, weather, blur, shake, etc. The second is security-related, which uses the model gradient to stack perturbation to attack, such as FGSM, PGD, SW, etc. The first is more general and more common, and also supports black box testing. The second is more targeted. The human eye is less likely to detect it, and it relies more on white box attacks. It is very difficult for an attacker to obtain model parameters, so the safety-related robustness test is more practical. Currently, we provide open-source version of robust tools for such evaluation. Perceptron Benchmark 10. The tool supports the testing of local models and cloud APIs. It uses 15 evaluation methods such as brightness, construction, rotation, noise, shake, occlusion, frost, rain, snow, etc. Because each method can set different thresholds, and the degree of image corruption and attack effect are also different, we use PSNR and SSIM as auxiliary evaluation standards. Take the ImageNet dataset as an example. In the angle rotation performance, especially the positive and negative 135 degrees, has an attack success rate of close to 70%, which indicates that the confrontation at this angle is the weakest. In the performance of noise, most of the label after the attack focus on several categories, which is particularly obvious in the salt and pepper noise. This weakness of the model that has been demonstrated through robustness tests can be targeted to use the adversarial training as mentioned before to compensate for it. Cloud service may still be subjective to adversarial attacks. Combined with the characteristic of adversarial attacks and the cloud service, the security development cycle for machine learning application is introduced. including adversarial detection, model defense, and robustness evaluation. The application of this method in the development will greatly improve the security of the model and help developers build more secure software. This is the end of my speech. We hope to have more communicate with friends who are interested in AI security. Thank you very much.